This video is going to discuss the area of figures. And basically, we're going to look at the basic figures that we normally run into when we're studying general mathematics. So we need to understand one thing, is that all figures, no matter what the figure is based on the same area formula for area, which is base times height. Everything. Everything is based on base times height. You just have to find it and determine what's going on and find those numbers and multiply them together. So what we're going to do is we're going to look at a bunch of different figures and we're going to show where the base and the height lie with each of these to help make it easier. Okay? So first we're going to start with our standard rectangle, right? And I think with the rectangle, it's really simple to see what each part is. We know that this part here on the bottom is the base, and this part here is the height. So it's really easy to find those numbers and then to just multiply them together. And once we multiply them together, we would have the area or this interior part, that measurement. Now, one of the things to remember about measurement when we're doing it in 2 dimensions is that whatever our measurement is, so let's say if it was in meters, that means because we have meters times meters, our answer would be meters squared. So we remember that our units will always be a squared unit. We're in 2 dimensions, square units. When we're in 3 dimensions, then it's cube units or to the third power. So we want to remember that our units are always going to be squared, whatever it is. Feet squared, meters squared, centimeters squared, inches squared, what have you. Okay, so let's continue to stay with this idea of the rectangle. And we know the rectangle has other representations as well that are similar to the rectangle. So, for example, the parallelogram. The parallelogram is similar to a rectangle except that it's leaning. So when we think about that it's leaning, we can see that the base is going to stay the same, but not the height, because now this is a slant. And because this is a slant, this does not necessarily measure how tall this is. So we got to go from the very top point to the bottom point. And this is where we would find that height. We could also find the height on the outside by drawing it to here. We want to always form a right angle when we are determining the height. So that's where we find the base. This is where we find the height. And then we would multiply them together. Now, whether this side is the base or this side is the base, it's the same thing because both of these measure exactly the same length. Because they measure exactly the same length, they could be considered, either one of those could be considered the base. Now, going back for a second to our rectangle, the same is true for the rectangle because this side could be the same as this side. And the height, this height, and this height are the same. So it doesn't matter where you get that height. Now we're going to look at a shape that's similar to a rectangle, but it's a special kind of rectangle. It's a special kind of rectangle where all the sides are equal. It's called a square. So when we look at a square, we need to remember that all sides are equal. Well, if all sides are equal, and I'm going to write base here and height because that's true how we do that. But we also know, again, talking about equal sides, we know that this side here is equal to this side here, and the base is equal to the base on this side. But since all the sides are the same, they're all equal to each other. Okay, so we could do one of two things. You know, you could say base times height, but you could say side times side. And this is why when you see this s squared as representing the area of a square, it's really they're showing that it is the base times the height. They're just using one variable only because all sides are the same. So sometimes you'll see that represented as how to find the area of the square. They'll say s squared, side squared. But we're still talking base and height. You're still going to get it sitting on something, and it's the height is measured by the right angle top to bottom. Okay, so we're still always going to see that. So now let's take a look at something that's similar to a square. It's called a rhombus. And the rhombus, it works the exact same way. We know that all the sides are equal, right? So if all the sides are equal, we're back to that s squared, or base times height, again, is still being represented because the measurements are all the same on all the sides. So in the beginning, talking about four-sided figures such as a rectangle, a parallelogram, a square, or a rhombus is pretty simple. But now let's dive a little deeper and let's get into a shape that we all know is familiar, but is still derived from the idea of this rectangle. So here I have a square, and you'll notice in the square I've colored two pieces. I've kind of cut the square in half from corner to corner so that you see two triangles. Well, these triangles, you can see that a triangle represents half of a square. So if I was to determine what is the measurement of a triangle, I know it's half of a square, which is base times height. That is why this is the representation for how we find the area of a triangle. We got to remember what our parts are. Again, here's our base, what it's sitting on, right? There's that right angle, and here's how tall it is. Now, not in all cases, in the case of a square, these are the same measurement, but usually we know our triangles are a little bit taller and maybe not exactly the same shape, but we can see that we can get this where it comes from. Why the representation for the area of a triangle is 1/2 the base times the height. Now, let's take a look at other types of triangles where we might be able to find that height right away. So here at the top, I have a triangle. And in this triangle here, we can still see this is the base because that's where it's sitting. But this is no longer a right angle. The right angle is here, right? It's right in here because that's where it goes straight. But the problem is yeah, that might be a right angle, but this isn't the tallest point of the triangle. This is out here. So what we're going to do is from this spot, we're going to come down and draw and find it there. So we will find our triangle height out here. And once again, we would just determine our formula, which is half, because I can get another triangle just like this, put it on the other side, and I can have a parallelogram, right? So, and it's base times height. So we know that to be true. Let me see if I can do it here. Let me get me one just like it. And flip it around. And you can see that I can build, see, there it is. There's that parallelogram. And because I only want half of one, I only want one, I get half the base times the height. Same thing's true here. We have the base, right? This is the base of this triangle. But we're looking for that right angle. Where's the top point? Well, we can see in this one, the top point is here. So if we draw our straight down here, and then there'll be the right angle there, this is where we would find the height. And once again, this would be where we would be able to do our formula of 1/2 whatever the quantity of the base is times the quantity of the height. And again, showing that we can do this, I'm going to clone this, flip it around so that you can see, there it is, coming in a little more. There it is. So now you can see where the base and the height comes into play, right? We can see that height right here. Remember, this is a slant. This outside part here, this is a slant. So we don't take the slant into consideration. The slant side, let me get a different color here. This is the slant side. The slant side, and there's a slant side up there too. These slant sides are not the tallest points. They are not from bottom to top. They do not form a right angle. So we don't use those sides to figure out how tall something is or the area. Remember, an area is what's going on inside. So we really want to keep an eye on that. We're just trying to find out what's happening inside the figure. So now let's take a look at some other figures. Okay, some different ones. Again, four-sided figures. These triangles are three-sided. Let's look at another four-sided figure I kind of skipped. Here I have a trapezoid. I should write that down. Trapezoid. Some people might not know what this is. Okay, and this is a trapezoid. Now, what's interesting with the trapezoid is that we can say the bottom is the base, but we know that, let me grab one of these here. Oops. Let me clone it. Okay, we know that a trapezoid can be found in either direction. Okay, so when we're looking at this, we could say that this could be a base here, but this also could be a base here, depending on which side it's sitting on. We also notice that the bases do not measure the same. They go from this end to this end. Here it's a little bit longer. Here it's a little bit shorter. Well, because of this issue with the bases, what we have to do is take something called the average. And if you remember what an average is that you would add together what you have. So I'll call this base 1 and base 2. So I'm going to take base 1 and base 2. And when you find the average of something, you divide it by how many things you have. So here I have 2 of them. I'm going to divide it by 2. So here's now, this is the part that's going to be considered when I'm trying to find base times height, right? Here is the base part right there. That's the base. Now the height, which we're going to multiply times the height again is really easy to find. We would do that by going to the topmost part and coming straight down to a right angle, okay? Either side. This measurement here, these right here would be considered the heights, the height of this trapezoid. Now, the same thing would be true if it was upside down. Your heights would be coming on the outside, right? Because you've got to create a right angle. So this is where we're going to see our height down here is in these outside lines. Now, remember, we also want to make sure that we understand this is not the height, that this is a slant. Remember, it's at an angle. So we've got slants on a trapezoid. There's a slant here, a slant here, there's another slant here, and one more here. So we've got to make sure we understand what our sides are. So when we're looking at what's our formula for finding the average in a trapezoid, it's this right here. We're going to add up the bases. We're going to divide it by 2 because we got to find that average, right? And now that we've got a base, we're going to take that number, multiply it times the height, and this here will give us our area for our trapezoid. So trapezoids are a little bit different in that we have to take an average. Now, not all trapezoids look like this. There are some trapezoids that look like this. So when we're looking at our trapezoid, this is called a right angled trapezoid. And the reason it's called that is because we can see the right angle right here. This is a lot easier to find height, isn't it? Because here's the height right there. We don't have to draw any lines. We know that whatever measurement is on this side is the height. Once again, there's your slant. So we don't really need the slant measurement when we're finding area. Those slant measurements only work on perimeter when you're finding the outside, but when we're looking for the inside, we just need these 2 measurements. So the next thing we need to find is the bases. And once again, here's base 1, here's base 2. So what you're going to do to find the area of a trapezoid, and I'm just going to draw a little thing here, is we're going to take the bases, add them up, divide by 2, and whatever number that is, we're going to multiply it times the height. And that's how we find the area of a trapezoid. Now let's get to the most interesting figure that a lot of people don't believe that base times height goes with it, and that is the circle. Now, we can determine the circle, right, top to bottom. We can find the top and go to the bottom and draw through the middle of this, and we can find the height. That's easy. But you really can't find the base because we know that a circle rotates, right? So what does it really sit on? So we've got to determine and figure out how does this space come in. So what we're going to do is we're going to do a little deconstruction of a circle so that we can understand a little bit more. So here I have a circle, and I hope we can agree that the outside measurement, and hopefully we've talked about this in class and you understand that the outside measurement here, remind ourselves that this is called the circumference. And we know that we find the circumference by the formula pi times diameter. Okay, so what we want to do then is take a look at a circle, and I'm going to divide this circle into 2. Okay, and what that does for me is it shows that this here, this is the diameter, right? And we know the diameter measures from one end of the circle to the other. And this diameter could also be considered the height of the circle. Even though this one's split across the middle, if I rotate this figure around, we can see that it would represent the height. So we know that we have a diameter. We know we have circumference. These have to come into play in order for us to find the area of the circle or what's inside the circle. So it's really hard to kind of get it to look like, remember I said everything is related to a rectangle, everything. So how do I make a circle look like a rectangle? Well, we're going to take a little bit of time here and see if we can get it there. I'm going to take this circle here, and what I'm going to do is I am going to change it and cut it into 6 pieces. Okay, and then I'm going to take these 3, if it'll let me. I'm going to probably be doing one at a time, but let me do that. So what I'm going to do is I'm going to fill this top part orange, and then I'm going to fill the bottom part green, just so we can make a little bit of a distinction. And then what we're going to do now is I'm going to take each piece out and I'm going to move it around. Now you can kind of see from where I'm starting, I'm trying to get this shape. I'm trying to get going here where it's starting to look a little bit like a rectangle. Okay, so it's starting to come across, come down, come down. So we're starting to see that rectangle, or actually a parallelogram, but it's still a little bumpy. We still need a little bit more. So let's do some more cuts. Let's do another one, and let's cut it a little bit more so that we can maybe start to see it just a little bit better. So let me divide this one. This time, let's go by 8. Okay, and I'm going to fill this top one by pink. And let's do the bottom one with purple. Let's try to complement each other. Okay. And so if I tear it apart again, I start to see it's looking more and more, a little bit more like that parallelogram. Let's try it again. This time I'm going to try and cut it already into 12 pieces. You see it already here in 12 pieces. And what I'm going to do is I'm going to color half of them in red, because the more pieces I have, the easier it is for me to see what's going on. Oops, I don't want to do purple. Let's do blue. Okay, so now we've got to keep this image in our head of what's going on, okay? We're going to take, remember that from here to here, we have a measurement, don't we? We know the whole side's called the diameter, but we got to remember this little piece here, this is called a radius, and that's going to come into play with us as well. So let's take these pieces, let's line them and alternate them upside down. Now we can kind of see that parallelogram going on. Okay, I think I have one here. Maybe I can get one a little bit to kind of show you how it's leaning. This is kind of just a standard one here, but we can kind of see this parallelogram going on in here. Okay, this little one I'm drawing over is a little bit more angled than that one there, but we can see what's happening. So now we've got to figure out, how do we get the formula for this? How does this come about? So let me take this and move it up, get rid of this guy down here, and let's start to figure out what's happening. So, because I said everything's related to base times height, right? So now in a parallelogram, okay, we know that this measurement here, going from the top to the bottom, right? This measurement here, which is the height, is our radius. Okay, so from the middle of the circle to the outside edge, that's called the radius. Now, this part here, this blue side, let's go back here and take a look one more time. We know that looking at it, we can see that, remember, all the way around is the circumference. Well, only this part is half of a circumference. So when we look here, we know that this measurement here is half the circumference. So if I follow the logic of base times height, right? Base times height. Really, what we're talking about here is the base, which is half of the circumference, and we're going to multiply that times the radius. Well, so far, That's looking okay, but we've got to get everything so that we don't have too many variables. And let's see if we can make it a little bit more understandable, because I'm sure you've never seen that before. So let's write down some information for us. We know that the circumference is pi times diameter. So let's replace this letter C here, and let's put in pi times diameter in that spot. So I'm going to write 1/2. We're keeping that. Instead of C, I'm going to write pi times diameter, and this radius is still coming with us, so I'm going to put an R. Now, still too many letters. We also know that a diameter is equal to 2 radiuses, right? So this time, what we're going to do is we're going to replace this diameter with 2 radiuses, and we're going to rewrite it once again. So let's rewrite. So now we have 1/2 times pi times 2 radiuses, 2 times r, right? 2r and r. So now I've got all this stuff. We want to make it a little bit simpler, okay? I know that 1/2 of 2 is 1. So this cancels and goes away. It just equals 1. And 1 times anything is just itself. So I don't need to worry about that. So now what do I have left? I have a pi, an r, and an r. So really what I'm left with is pi r squared. And guess what? That's the formula for the area of a circle. So you can see that this formula for the area of a circle is related to base times height, right? We said everything is related to base times height, and we showed that it did. We can take it and we can derive the formula, and that's why the area of a circle is considered pi times radius squared, because it is the base times the height. So we need to, excuse me, we need to look at a couple of more figures, just in case we're going to work on some composite figures. So let's take a look at this. Here we have a half a circle. So we know that if I want a half of a circle, we want half of the area, right? We want this area in here. We know that a circle is pi r squared. So we need just 1/2 times pi times r to the second power. So this would be our area of our half circle. And just so you know, a half circle is also called a hemisphere. So in case you see that word, we talk about a hemisphere or half a circle. Now, you can apply everything we've talked about right now, even into what we call the gons. I'm sure you guys have seen the gons. The gons are things like this. Here, this first one's a pentagon. This one has 6 sides, so it's a hexagon. And this one has 8 sides. It's an octagon. So pentagon 5 sides, hexagon 6 sides, and an octagon has 8 sides. So what do we know? Well, here's the thing we know about them. We know that a pentagon has 5 sides to it, but it's also made up of 5 triangles. Well, because it's made up of 5 triangles, and we know that the formula for a triangle is 1/2 pi r, excuse me, I said pi, I didn't mean that, 1/2 base times height, right? And because there are 5 triangles, the formula for finding a pentagon is you need 5 of these. So I need 5 times 1/2 times the base times the height. Okay, here's your base, right? And here's your height. Let me get a different color in here. Kind of break it up a little bit. Remember that right angle, right? That's your height. Here's your base down here. Okay, so you take those numbers, you put it in, and guess what? All you're doing is saying, hey, this is what the one triangle is, and I need 5 because it's a pentagon, so I'm going to multiply times 5. The same is true for a hexagon. Okay, a hexagon we can cut up into 6 triangles. So we would just say it is 6 times 1/2 times the base times the height. And then same thing for an octagon. Okay, an octagon, this would be 8 times 1/2 times the base times the height. And that's how you would find the areas in gons. And these are regular polygons, not strange looking hexagons, octagons, stuff like that, but standard regular polygons. So hopefully this gives you a little idea of area and how all of area is derived from the formula base times height.